All right, so we're talking about this inductance in circuits. We talked about the fact that we're in a DC circuit, because it's just easier to talk DC because it's on and off. But the same thing is going to happen in an AC circuit where it's constantly changing. But we're just kind of, walking here before we run. So when we turn on the circuit and it's got a coil, so it takes some time for now the current to build up to maximum. As we're in a purely resistive, just resistors, boom, instantaneous, and then we're there. Now it's going to take a while to build up, then we're there. And then we shut it off, it's going to take a while before it shuts down, then we're there. If we had, somebody's got to remember to bring a battery in tomorrow, one of those 12-volt batteries. And I can show you with at least a capacitor, you can show you how it takes a while with the big capacitor, because it's the same thing. But opposite in a way. But you can see if we put a little incandescent light, the light would take a second to come on if it was a big enough coil before it'd be really bright. And then we shut it off, it would take a while for it to kind of work its way down. Us old guys, remember the old TVs that would do that. You turn it on, it'd take a while for it to come on. You turn it off, it'd take a while for it to go off. So it takes a while. And you're asking yourself, how long does it take? Let me see. The greater the inductance, the greater the inductance, the longer it takes. Why did it do that? Oh, I see. There's buttons. All right. I probably could just say that, be done with it. But that wouldn't be any fun. So it takes longer. Well, how much longer? How do they figure this out? What does it do? Well, the amount of time it takes is 5 time constants. Now, that's not how many seconds. It's 5 time constants. Then you can add the seconds in later. So the amount of time it takes, do this, the amount of time it takes for current to reach maximum is based on time constants. Is based on time constants. All right, takeaway from this is how many time constants? 5. So it takes, rewrite this a little bit. 5, it takes, let's see. Well, I'll just go with this. 1 time constant. 1 time constant is the time it takes. Let me see. The time it takes. The constant is the time it takes for current to increase or decrease, because it's on the way down too, 63.2% of the previous value. I'll explain that in a second. It takes 5 time constants to equal full value or zero value, which is full value, which is greater than greater than 99%. 99% is considered good enough, close enough, or 0, less than 1%. So it's considered all the way maximum if it reaches what percent? 99, or all the way to 0, which is less than 1%. And it takes how many time constants? 5 of these. And the 5 time constants is based on 63.2%. How would you like to be the guy who thought that one up?
Will that be allowed right now?
Probably not.
No, cool.
Why 5? Why 5? Well, if you have your calculator out, and we said, what is full value?
Greater than 99.
What is the fullest of full value then we could have? 100%. So if we had 100%, and we're going to decrease, we're going to go down. We have 100%, and the difference is how much? 63.2%. So if I have 100%, or if I have a quantity of 100, we'll just say 100 is full because it's easier just to say that. 100, so we'll get rid of the percent sign. We'll just say 100 is the max. It's full, like a percent. And we subtract 63.2%. We get how much?
36.8.
We get 36.8. Well, if I have 36.8 and I subtract 63.2%, I am left with do you want me just to tell you? You know how to get that? It's a little bit, I don't know, these calculators are a bit slower. If you have a financial calculator, it's easy. You can actually just put 36.8 minus 2%. So if to figure that out, you'd say 36.8 times 63.2% equals, that would be,
So you're trying to get 2 time constants there.
yes, this is time constant 1. So we went from 100 all the way down to 36.8. Now it's at 36.8, and we got to subtract 63.2%, which 63.2% of this number right here is, would you guys get, it's like 23? 23.26, somewhere around that. You're going to end up with 13.54. Did I lose everybody here?
So we're going to do 36.8
Hang on.
times 0.632.
Start all over again. 'Cause it doesn't do me any good to go fast. All right, try it again. We have a full value. We've gone all the way up. The inductor is completely charged up. And we're going to say, how many time constants does it take to go to 0? Got it?
Got it.
Because it makes more sense than trying to go up. Trust me on this one. So full is 100%, but we're not going to say percent. We'll just say 100. So it's fully charged up, 100%. We'll just say 100. Got it? Okay. And a time constant is an increase or decrease of 63.2% of that number. So 100 times 63.2 equals percent equals 63.2, right? So then it becomes 100 minus 63.2 equals 36.8. Everybody follow me so far?
Yes. That's how much is left.
That's how much is left. The light's dimming down. So we have 36.8, and we got to subtract 36.8 times 63.2%, which equals, so 36.8 times 63.2% equals, that number is?
15.55.
No.
23.256.
23.2, we'll say 26. So we have 23, so it's 36.8 minus 23.26 equals 36.8 minus 23.26 equals 13.54. Got it?
Got it.
The light got a little bit dimmer now. Went from 100 to 36.8. 36.8, 13.54. But notice how it's not linear, really. I mean, it's like a lot, and then it's then a little bit by little bit. So now we have 13.54. Well, we got to subtract 13.54 times 63.2%, which equals 13.54 minus, times 63.2% equals 8.56 about. So it becomes 13.54 minus 8.56 is going to equal 4.98. Well, now we have 4.98 left, and we've got to subtract 4.98 times 63.2% equals 3.15. So we've got to have 4.98 minus 3.15 equals, I'm just looking at my notes here, 1.83. All right, now we have 1.83 left, and we're going to subtract 1.83 times 63.2%, which is going to equal 1.16. I'm just going to trust you on this. So 1.83 minus 1.86 equals, and I have my notes, we should be ending up with about 0.67, which is less than 1%. So how many time constants did we take? 2, 3, 4. 1, 2, 3, 4, 5 time constants. Now, if we did it the other way, we turn the switch back on. Well, we can't go the other way because we'd start with 0 and go, whoa, what is 0? Times the answer would be 0. But we go from 0.67 to 1.83 to 4.98 to 13.54 to, oops, I should be looking at the other column. 13.54, 36.8, 100. See, it's going to build up. So how many time constants does it take? 5. Now, that didn't tell us how long it is. It just takes 5 of these. And what? You're like, I hate this place.
I get the simplicity of this.
Yeah, so it takes 5 of them. How many does it take? 5. How long is each one? I don't know, it takes 5 of them, though. So how many time constants does it take? 5, okay. All right, so time constant. Time constant is proportional to inductance which means takes how many of them? 5. How long is each one? I don't know, but the more inductance you have, the more henries, the longer each time constant is going to be, proportional to inductance. And inversely, proportional to resistance. So the more resistance, well, we'll do this, more inductance equals what? Longer or shorter?
Longer.
Okay. More resistance equals shorter. And that's represented by the formula, which we don't have to worry about. Time constant equals inductance divided by resistance. but we're not going to do that. Even though I've got it in here. Example, R is 10 ohms and inductance 2 henries. How long is each time constant? We could do it real quick. Just give you a break.
5.
All right, 5. So we've got to do it this way. So R1 equals, what did I say? 10 ohms. And inductor 1 equals 2 henries. Well, then how long is each time constant? Well, if a time constant is inductance, which is 2, divided by resistance, which is 10, then the answer is 0.02. So it's a time constant of 0.02. Well, it takes how many time constants? What's that? 0.2. 0.2, sorry. 0.2. Takes 0.2. So it takes 0.2 seconds is one time constant. How many time constants? So times 5 equals 1 second. So it would take a full second for it to go from 0 all the way up or from all the way up back to 0.
So the 0.2 is seconds. So that's
Seconds, yes. Time constant in seconds equals inductance divided by resistance. All this to say, with an inductor, voltage will be instantaneous but it takes time for the current to build up, to build up. Therefore, in an inductive circuit, an inductive circuit is a circuit that has more inductance than anything else. If it's got more resistors, then technically it's a resistive circuit. If it has more capacitance, then technically it's more capacitive. Well, actually, we're going to kind of change that to where it's either got more inductance or more capacitance. So in a circuit that is more inductance, has more inductors than anything else, the voltage leads the current, which is Eli. The voltage leads the current. Current is behind. But in a DC circuit, this only happens when? What's that? Beginning and the end. Start up, shut down. But in an AC circuit, sinusoidal circuit, it's constantly happening. So current changes constantly, therefore the effects of inductance happen constantly. So do this. Inductive AC circuit. Now, in an AC circuit, having a hard time adjusting to this new pad. Circuit, current changes, current and voltage change constantly. Therefore, the effects happen effects happen constantly. And since, and we know this, the counter EMF, CEMF, happens, I should say the greatest, the most CEMF, or greatest CEMF, happens in a AC circuit, right? AC circuit. Here's my zero line. We talk about the coil, we talk about the buildup. When is the counter EMF the most? Or even we talk about the generator. When was the voltage produced the highest, the current flow? What's that? The peaks. At the peak. So is the greatest change here? Let me write this a little bit different. All right, let's think about this. So what produced, go back to the magnet and the wire, what produced voltage, which then produced current? Motion. What produced the highest amount? Little motion, more motion?
More motion.
So the more motion I have, the more counter EMF I would have, right? Okay, so where is the greatest change on this chart?
Right across is 0.
So I kind of drew it sideways. So is the greatest change from here to here? No. So if we look at it, there's really very little change right here. There's not a lot of change here, especially the way I drew it. Not much change here. So the greatest change really takes place kind of through this area where it's falling down and picking back up. So therefore the greatest change happens right there, right there, right there, which is going to be how many degrees? 0 degrees. And this is at 180. And this is at 360 or 0. So the greatest change is always going to happen there. That's going to be very important when we talk about some other things, magnetos. So Lenz's law, CMF follows Lenz's law and opposes current change 90 degrees later. All right, we'll just go to this one. In a purely inductive circuit, current lags voltage by 90 degrees. And counter EMF is 180 degrees out of phase, which we already said before, out of phase. And if you can remember that, that's fantastic. If you can't, that's fine. But what I want you to do is understand this relationship of relative movement in wire and what causes the voltage and the current to flow, and the fact that when you have an inductor and you apply forward voltage to it, it's going to oppose that voltage and it's going to slow down the buildup. And then when it does finally build up, it's going to go the other way, and as it goes the other way, this collapse is going to create a counter EMF in the coil, which then opposes the collapse, and so it's constantly opposing whatever it's supposed to be doing. If it's supposed to be building, it doesn't want to. It's like my kids. If it's supposed to be collapsing, it doesn't want to. Whatever it's supposed to do, it doesn't want to. It takes how long? Right, which isn't really important, but so it's like, all right. So how are we going to compute this? I think this is number 13. Computing. Yeah.
What was the point earlier, since mostly CEMF happens?
What is the point behind it?
Well, like what's
0, 180, 360.
What is my point behind 0, 180, 360?
No, you said since most counter EMF happens, and then you drew that.
Oh, I didn't. I didn't finish it.
Assumed you-
I just drew it out. Let me see. Okay, so let me see. I don't know. Oh, because I was changing it. Okay, since most counter EMF happens with the greatest change, in applied voltage. I'm making stuff up as I go. The most or highest CEMF is at 0, 180, and 360 degrees, which is really the same, 0 and 360, or 0, 180, 0, 180. And the whole point behind that is to realize that the greatest change is not at the peaks or the valleys, because there really isn't much change per time there. The greatest change per time happens as it's going through 0, which is going to become something that's going to be very important at some point. Computing inductance in a circuit. Well, here's some good luck for you. It is done exactly like resistors. Are calculated exactly like resistors are calculated. So if you have inductors in series, then L total is going to equal L1.
Plus L2.
Oh my gosh, you guys remembered. Okay, L plus L3, on and on and on. In series, parallel. L total equals L1
equals L2 equals
over 1. Oops, I screwed up with my spacing here. LT equals 1 over L1 plus 1 over L2 plus 1 over L3, all of that with the 1 over. So just like resistors. That was easy. This is assuming that the inductors are placed far enough. I should probably write this. Can I move?
Yes.
What?
1 second, just catching up.
Well, it's just like resistors.
Yeah, nice.
Great. Could you write down what resistors are, please? This is assuming that the inductors are placed far enough away from each other so there's not mutual inductance from each one of the resistors.
So if they're placed too close enough, do they just become one big?
Yes. If you stack them all together, then it's like one big one and all bets are off. Then you can't really add them up because it's like, well, wait a minute. They're all like one big inductor, and so that's bad. All right, so assuming. Assuming the inductors are placed far enough away from each other to not create mutual induction. To not create mutual induction. Is it 13 I'm on now?
14.
14, thank you. All right, 14. 14. So now now we've learned all about inductors and we've learned how to, add them up, but we're going to look at inductive reactance.
Is mutual induction, you say it's got to be,
Well-
assuming that it's placed far enough away?
You have two coils and this one's expanding. It's going
Right.
to expand across this one.
So is that,
That's bad.
right, so the
Well-
distance that is considered far enough away, is it based on how large the coil is?
I'm sure it is, yeah. I don't have a formula for that, but yeah, definitely.
It's 5 time constants.
I was gonna say that, but it's gotta be 5 distances apart. Okay, so with resistors, we're lucky because we have just resistance, right? And so we can look at the color code and we can measure it with an ohm meter, and there's no problem. Resistance is kind of an easy one to figure out. But we have inductive reactance. Well, inductive reactance, we take what we just learned, and we learn that it takes a while, 5 time constants, for this coil is going to oppose current, right? So voltage is going to build up, it's going to oppose current, which is like resistance. So there is resistance within these inductors, but it's not called resistance per se. It's called inductive reactance, which is what does it do to the circuit. So we're going to look at that like we'd be looking sort of at resistance. So inductive reactance inductive reactance is the effect of inductance on a circuit. Is the effect of inductance on a circuit. It is, let's say measured. I should say expressed. Yeah, not measured. Expressed. Expressed in ohms. Yay, back to normal. But due to phase shift, is not considered resistance. And that's going to be important because when we think about AC and Ohm's law, everything holds true for Ohm's law with the exception of when you get down to the circuit, you just can't do 3 things and go, well, I've got the voltage and I got the amperage, therefore the resistance, including inductive reactance, capacitive reactance, and resistance all put together, equals E divided by I, therefore there's R. It is not like that. Because you're going to have inductive reactance, but it's not quite resistance. You're going to have inductive capacitive reactance, but it's not quite resistance. And you're going to have resistance, which is exactly resistance. So I'm just telling you where we're going. So when you get all done, don't go, well, wait a minute. E divided by I doesn't equal R. It's not going to. First time I did that and I got down the end, I'm like, what the hell did I do wrong? I'm like, oh, that's right. So that's why I'm kind of stressing that point now. So, yeah, I should have went measured. I don't know. I don't like the word measured, but it makes more sense. I'll have to think of a better word for that because I'm going to use expressed right here. So, expressed as X of L. X of L. And inductive reactance is proportional to the inductance and the frequency. Proportional to the inductance and frequency. Which does it say? Which is to say, if the inductance goes up, then the X of L goes up. If frequency goes up, then X of L goes up. And if you think it through, should you decide to, that should make sense. The more inductance you have, the bigger the coil. And we go back to what makes up inductance. Well, we've got a coil, we've got a core that is highly permeable. Then that's going to make it so that it takes longer to build up. If we have frequency goes up, that's more changes per second. That means that more changes means the faster it's changing, the faster it's changing, the faster it cuts across the magnetic lines of flux, cut across the wire, which means you're going to have more of the EMF, so everything should make sense in that way. Now we're going to cover a lot of formulas. I've thrown some formulas up here so far this whole week, and I don't think there's anything I've put up there yet this week that you need to remember. Now you do. And the way this is going to go is that we're going to have a lot of formulas, and you're responsible for knowing what that formula is. Like this next formula is going to be X of L equals 2 pi FL. I'm going to write that. You're going to be responsible to know what it is, but when we go to take the test on Friday, I'm going to pull up this right here, and I'm going to say, what formulas do you guys want up on the board? And you would say, well, I want X of L equals 2 pi FL. I'm going to write X of L. I can tell you what it is. You need to know what it is. And you'll know, trust me. It's not a problem. So don't think you have to memorize any formulas. I'm not about that. So, all right. So the formula for figuring this out is, I just said it like 3 times, X of L equals 2 pi FL. Where X of L equals what? That's right, inductive reactance. Very good. Inductive reactance, ohms. F is frequency, also known as hertz, Hz. And L is inductance. Which is L, or henries. So if I had an example, and is everybody caught up? Everybody with me?
Yes.
All right. If I said, what is X of L if the frequency, if we have 60 hertz and 7 henries, what is X of L? So X of L equals 2 pi FL. So X of L equals 2 times pi times 60 times 7.
2,639 ohms.
So X of L equals, how much?
2,639.
Okay, we want to be, he's correct. Very careful about rounding, because this number is going to carry to another, which is going to carry to another, which is going to carry to another. So the more you round, the worse it's going to get when you get to the end.
2,638.937.
It's entirely up to you how far you want to go out. So you've got to write it down. You've got to plug it back into the calculator. 2638.9 ohms. All right, that's about all I got to say about inductors. Speak now or forever hold your peace. Everybody understands inductors. So here's some big takeaways about inductors. Well, I think I kind of beat it to death about inductors. Take time to build up, take time to collapse. It's the inductance is based upon its properties, how many turns you have, what the core is made out of. Certainly the effect of the circuit is going to be based upon then how the coil is made, how many henries it is, and what the frequency is. So if I increase the frequency, it's going to have more of an effect on the circuit. It's going to delay it more and more. What's it going to delay? What's the outcome here?
Delays current.
I'll give you a hint. What does Eli say? So the more X of L I have, the more inductive reactance I have, what is going to happen to the circuit?
Out of phase.
It's going to get more out of phase. What's going to happen?
The voltage is going to beat the current.
The voltage is going to be way over here, and the current is going to be way over there. So if I can draw it nicely, it would look like if here's voltage. This is a hard one. Voltage then would be out of phase, way out of phase with the current. So the current would be up to 90 degrees out. So it starts way over here and goes up. And so it's now out of phase. So it's going to be like 0 over here. So it's 90 degrees out. So you don't want that. That is not an efficient circuit at all. And it's going to create heat and inefficiency, and it's bad. So we got to, when we look at this, we analyze that, we go, wow, our X of L is pretty bad. We don't want that. We needed to bring it back the other way. Well, we haven't talked about that yet, but we certainly know at this point that X of L is there. It's 26.38.9 ohms in this case. We can calculate it, and we know that it's, I want to say bad. It's not necessarily bad, but at this point, we know that it has had a very negative effect on the circuit, right? Okay. Everybody's good with that? All right.
We have to let it marinate for a second.
Okay, I'm going to move on, though.
All
I think I'm at point 15.
right. Yes.
All right, let's talk about capacitors. Capacitors. Capacitor is a device that stores electricity. So a capacitor is a device that stores electricity. Or I guess more appropriately, it stores electrons. I could say it's like an electrical accumulator. Now I have to explain what an accumulator is, so I should have never done that. We use accumulators in hydraulic systems. And like an example would be, you have a hydraulic system. Well, just inside of the system, like you have a pump and then a line that would maybe go over to a flap actuator. So, it makes the flap go down and back up. But right in between the two, kind of parallel off of it, you would put this like a cylinder. And the cylinder has a whole bunch of fluid in it. And it's got a piston with a big old spring in it. And so when the hydraulic pump pumps up, it pushes this all the way down. And then that whole cylinder is just full of pressure because that spring is pressing on it. So when the flaps start to go down and suck a lot of hydraulic fluid, this thing will press up on it, take that big storage with that spring and just kind of supercharge that down, right? It's a storage of something. So it's the same thing with the capacitor. Or I could have said it's like a little battery that lasts not very long at all. It lasts about 5 time constants, if you will. So, all right, so it consists of two conductors, which are actually plates that hold an electrical charge. Now, things I shouldn't probably tell you. You'll figure it out.
What's it do?
Capacitors can provide you with a lot of entertainment.
Like when you
charge them up and you toss them to your phone.
When you charge them up, they hold one hell of a charge. These are nasty monsters. I think this one came out of my AC unit at home. If somebody remembers to bring a battery tomorrow, we'll play with that one. But this is one that is, these are the plates right here. So you can see they're separated by a dielectric, which is paper, and they're rolled up in there and they're not supposed to touch. So I don't know if I rolled this out, it'd probably make it well past the door so you can see how much those plates are. And they store a pretty good charge. Now the ones that you might see in the magnetos are about that tall and about, I don't know, as big around as my thumb. They will hold thousands of volts. Just off the top of my head, I don't know, that thing will probably hold 10, 15,000 volts. And you can tell that because when you charge them up really well and you take the lead and you bring it back around to ground it out, it will have one hell of a spark. You can hear it across the room. So that's some massive voltage. So yes, you charge it up and then very carefully hand it to somebody so that both the lead and the case touch their hand at the same time. They will definitely feel it. So it holds a, so be careful. What's that?
It'll be warm.
It doesn't get warm, it just snaps. Yeah.
So it's an electronic mousetrap.
Yes. So it consists of two plates that hold an electrical charge, two plates, electrical charge, and are separated by an insulator called a dielectric. Dielectric. The ability of a capacitor to store electricity is known as capacitance. We'll finish with this sentence here. The ability of is the word I wanted. The ability of a capacitor to store electricity, we'll say electrons, store electrons is known as capacitance. Capacitance, and is measured in farads. Remember that guy? Michael Faraday. F. Farads. F. From Michael Faraday. All right, that's a good place to end it right there. I think it's not really be a better place to just keep going.